The Moon's formation began with a dramatic event around 4.5 billion years ago. A Mars-sized body called Theia collided with Earth in a massive impact. The force of the crash was so intense that it sent debris flying into space. This debris eventually came together to form the Moon. Imagine Earth as it was back then. It was still in its early stages of development, with molten rock covering its surface. Theia, a planet-sized object, was on a collision course with Earth. When the two bodies collided, it was more than just a crash. It was a violent explosion. The impact was so powerful that parts of both Earth and Theia were ejected into space. This ejected material formed a cloud of debris around Earth. Over time, the pieces of this debris started to clump together, pulled by gravity. Some of the material from the impact fell back toward Earth, but much of it remained in orbit. Slowly, this cloud of debris began to gather into a single, larger mass. Eventually, this mass became the Moon. The process of forming them, it took millions of years for the debris to come together. Early on, the Moon would have been a hot ball of rock, constantly bombarded by leftover space debris. Over time, it cooled down, solidifying into the Moon we see today. However, this process did not stop at just creating a new satellite for Earth. It also had a profound effect on both the Moon and Earth. The collision and the resulting debris likely caused the Moon to have a composition that is very similar to Earth's outer layers. The Moon and Earth share many common materials, like silicate rocks, and both bodies have similar isotopic signatures. This suggests that the debris that formed the Moon came mostly from Earth rather than Theia. In fact, the Moon's composition supports the idea that Theia was only partially involved in the material that ended up on the Moon. Think of it like a pancake batter where you mix a bit of flour from two different sources. And when you make the pancake, it's hard to tell which flour came from which bag. In this case, the batter is the Moon, and the flour is the debris from Earth and Theia. This is why the Moon's composition is so closely related to Earth's, even though Theia was the body that caused the impact. The gravitational forces between Earth and the Moon also shaped both bodies in unique ways. Over time, the Moon's gravity has affected Earth's rotation. The Moon's pull on Earth causes tides, and this interaction has also slowed Earth's rotation. Early on, Earth likely spun much faster than it does now. The presence of the Moon has acted like a brake, gradually slowing Earth's spin. If the Moon had never formed, Earth would have a much shorter day, and the tides would be vastly different. On the Moon, the effects of the collision can still be seen. The Moon's surface is covered in craters, many of which were formed by smaller objects that collided with the Moon after the original impact. The lack of an atmosphere on the Moon means there is no weather to erode these craters, so they remain intact. These craters serve as a record of the harsh conditions the Moon experienced during its early years. The impact that formed the Moon didn't just create a new satellite, it also set in motion a chain of events that would change both Earth and the Moon. The collision was so powerful that it left a lasting mark on both planets. The Earth we know today, with its stable rotation and moderate climate, owes much of its characteristics to the Moon's formation. Likewise, the Moon itself, with its unique features and its close relationship with Earth, would never have existed without this ancient impact. The Moon, now a constant companion in the sky, is the result of a colossal collision that happened billions of years ago, and it continues to influence life on Earth in ways we might not always see but still feel. The Moon is about 4.5 billion years old, which makes it slightly younger than Earth. This age is based on scientific studies that have looked at both rocks brought back from the Moon and meteorites that have landed on Earth. By examining these rocks, scientists can determine when they were formed and how long the Moon has been around. One way to figure out the Moon's age is by looking at the age of the rocks found on its surface. During the Apollo missions, astronauts brought back samples of moon rock. By using a method called radiometric dating, scientists measure the decay of certain elements in the rocks. This decay happens at a steady rate, and it allows scientists to calculate the age of the rock. The oldest rocks collected by the Apollo missions are about 4.4 billion years old, which tells us that the Moon has been around for a long time. The age of the Moon is closely tied to the formation of the solar system. Both Earth and the Moon formed from the same cloud of dust and gas that surrounded the Sunday. This cloud collapsed under its own gravity, and over time it formed the planets, including Earth. The Moon's formation, as we know, occurred when a Mars-sized body collided with Earth. The debris from that impact eventually came together to form the Moon. This event likely took place shortly after the solar system itself formed, which means the Moon's age is just a bit younger than Earth's. Scientists also study meteorites, which are bits of rock from the Moon that have made their way to Earth. These meteorites provide another clue about the Moon's age. By looking at the age of the Moon rocks found on Earth, scientists can compare them to the samples taken during the Apollo missions. This helps confirm that the Moon is about 4.5 billion years old. The age of the Moon is also reflected in its surface. The Moon's surface is covered in craters, many of which are billions of years old. These craters were caused by smaller objects that hit the Moon over the course of its history. Since the Moon has no atmosphere, these craters have not been erased by weather or erosion as they would be on Earth. This gives scientists a clear view of the Moon's long history. Some of the craters are so old that they are difficult to measure accurately, but their presence is another sign that the Moon is very ancient. Another factor in understanding the Moon's age comes from studying the Earth-Moon system. The Moon affects Earth in many ways, one of the most obvious being the tides. The gravitational pull of the Moon causes the ocean's water to rise and fall. But the Moon's pull on Earth also affects the length of the day. Early in the Moon's history, Earth's day was much shorter than it is today. The Moon's gravity slowly slowed Earth's rotation, lengthening the day over billions of years. This gradual process of slowing Earth's rotation provides another clue about the Moon's age. By studying how much Earth's day has lengthened, scientists can estimate when the Moon formed. The Moon's age also plays a role in our understanding of the early solar system. Early on, the Moon was likely covered by molten rock. Over time, it cooled and solidified to form the surface we see today. However, the Moon also experienced a period of intense bombardment. Smaller objects from space hit the Moon's surface, creating craters and shaping its appearance. This period, called the Late Heavy Bombardment, likely happened around 4 billion years ago. By studying these events, scientists can learn more about the conditions of the early solar system and the Moon's history. The Moon's age also tells us a lot about the history of Earth itself. When the Moon was formed, Earth was still in a molten state. The collision that created the Moon changed the Earth's environment and set in motion the processes that would shape our planet's development. The Earth and Moon are deeply connected, with the Moon playing a crucial role in stabilizing Earth's tilt and influencing its climate. The age of the Moon reminds us that both Earth and its companion have a shared history that dates back billions of years. The Moon is slowly moving away from Earth, a process that happens because of tidal forces. Every year, the Moon drifts about 3.8 centimeters farther from our planet. This movement is not noticeable in our daily lives, but it is a gradual change that has been happening for billions of years. The reason for this movement lies in the way the Moon's gravity affects Earth. The Moon's pull on Earth creates the tides, the rise and fall of ocean water. As the Moon's gravity pulls on Earth, it creates a bulge in the oceans. This bulge is what causes high tides. The Earth's rotation causes this bulge to move, but because the Moon's gravity is pulling it, the bulge moves slightly ahead of the Moon. This creates a kind of tug-of-war between Earth and the Moon. Earth is trying to pull the moon closer, but the moon is pulling on Earth's oceans. This results in the transfer of Earth's rotational energy to the moon. In simple terms, as Earth spins, some of its energy is passed on to the moon, pushing it farther away. At the same time, Earth's rotation slows down a tiny bit as it loses energy. Imagine spinning a basketball on your finger. If you move your finger slightly, the ball moves in the same direction. Similarly, the energy Earth loses because of the tidal forces is transferred to the moon, causing it to move away. This process happens at a very slow rate, but over millions and billions of years, the effects add up. This gradual movement has been happening for a long time. Scientists have studied ancient tidal patterns, and from this data, they estimate that the moon was much closer to Earth in the past. In fact, billions of years ago, the moon was probably much closer than it is now. Over time, it has slowly moved away due to the tidal forces at work. As the moon moves away, Earth's day also gets longer. The transfer of energy from Earth to the moon slows down the Earth's rotation. This means that Earth's days were much shorter in the distant past. For example, when the moon first formed, a day on Earth might have lasted only 6 hours. Today, it lasts 24 hours, and in the future, it will continue to lengthen. This is not a quick process, though. The moon's drift of 3.8 centimeters per year may seem small, but it adds up over time. In the distant future, it could have a noticeable effect. Eventually, if the moon keeps moving away at this rate, Earth could end up without its moon. However, this won't happen for a very long time, billions of years into the future. Long before that happens, the Sunday will have evolved into a red giant, changing conditions on Earth in ways that make this concern irrelevant. For now, though, the moon continues to drift away and Earth's rotation continues to slow. This slow dance between Earth and the moon, driven by tidal forces, has been happening for billions of years and will continue for billions more. Though the change is too slow to see in a single lifetime, the effects are clear in the long-term history of the Earth-Moon system. The moon's gravity is much weaker than Earth's. It's only about 1/6 of what we experience here on Earth. This difference in gravity is why astronauts can jump so high on the moon compared to how they jump on Earth. Gravity is the force that pulls objects toward each other. On Earth, gravity pulls everything toward the center of the planet, which is why we stay grounded. The strength of gravity depends on two things: the mass of the object and the distance from its center. Earth is much larger and more massive than the moon, so its gravity is stronger. The moon, being smaller and lighter, has weaker gravity. To understand this, imagine trying to jump on Earth. Your body is pulled down by Earth's strong gravity, which makes it harder to lift off the ground. If you jump, you only go a short distance before gravity pulls you back down. Now, think of jumping on the moon. Because the moon's gravity is weaker, it doesn't pull you down as strongly. So when astronauts jump, they can go much higher and stay in the air longer before gravity brings them back down. For example, if an astronaut on Earth can jump about 1 foot high, on the moon, they might be able to jump 6 feet or more. This makes it look like they are floating or moving in slow motion compared to how we see people jump on Earth. This difference in gravity also affects how things move on the moon. Without the strong pull of gravity to slow them down, objects on the moon don't fall. If you dropped a hammer and a feather on the moon, they would hit the surface at the same time, unlike on Earth where the feather would fall much slower because of air resistance. The lack of atmosphere on the moon also means there is no air to slow things down. The moon's weak gravity also has other effects. For instance, it doesn't hold on to an atmosphere like Earth does. The moon's gravity is simply too weak to keep gases from escaping into space, which is why there is no breathable air on the moon. Without an atmosphere, there is also no weather or winds, which means the moon's surface is much more stable over time. For astronauts, the weaker gravity on the moon makes things both easier and harder. On one hand, it's easier to carry heavy equipment because you weigh less. But the low gravity also means that movements are different. For example, astronauts have to adjust their steps and movements to avoid jumping too high or floating too far. In the long run, the moon's gravity also affects the way objects, including astronauts, stay in motion. Since there is less gravitational pull, objects don't slow down as quickly as they would on Earth. If an astronaut were to push off a surface, they would keep moving longer, since there's less gravity to stop them. This difference in gravity also plays a role in the way the moon interacts with Earth. The moon's gravity affects Earth in many ways, especially through the tides. The same force that lets astronauts jump high also pulls the oceans on Earth, causing the water to rise and fall. Over time, the moon's gravity has been a key factor in shaping Earth's environment. The moon's weaker gravity is one of the main reasons why we can see astronauts jump so high during the Apollo missions. The low pull on their bodies makes movements on the moon appear almost like floating, giving a unique and surreal feel to the experience. The dark side of the moon is a term that often causes confusion. In reality, there is no permanently dark side of the moon. Both sides of the moon receive sunlight at different times. The moon rotates on its axis, just like Earth. But it does so in a way that keeps one side always facing Earth. This means the other side, the one facing away from us, is often referred to as the far side of the moon, not the dark side. The reason we only see one side of the moon has to do with a phenomenon called synchronous rotation. This means the moon takes the same amount of time to rotate on its axis as it does to orbit Earth. This is why one side is always facing us. It's like if you were spinning around while walking in a circle, always keeping your face turned toward the center. In the moon's case, that center is Earth. Because of this, we never get to see the far side from Earth, but it still gets plenty of sunlight. The moon completes a full orbit around Earth in about 27.3 days. During this time, the same side always faces Earth while the other side. As the moon orbits, both sides are illuminated by the sunday. When one side is in daylight, the other is in darkness. And when the side facing Earth is in darkness, the far side is in daylight. This cycle repeats as the moon orbits Earth. The far side of the moon was first seen by humans in 1959, when the Soviet spacecraft Luna 3 took. Before that, no one had ever seen what it looked like. There was a lot of mystery surrounding the far side, and people assumed it was somehow different from the side we could see. But when the images came back, it was clear that the far side was not all that different. The main difference is that it has more craters and fewer large dark plains known as maria, compared to the near side that faces Earth. The far side's surface is rougher and more heavily cratered, which has led to some interesting theories about its formation. Scientists believe the far side's crust is thicker than the near side's, possibly because of a lack of the large volcanic activity that created the dark plains on the near side. However, both sides of the moon share similar features, such as craters and mountains. Despite its name, the far side is not dark, in the sense of being in constant shadow. In fact, it experiences daylight and night in the same way as the near side, just at different times. The term dark side comes from early misconceptions. The far side of the moon is simply the part we cannot see from Earth. Astronauts who went to the moon during the Apollo missions were able to see the far side when they circled the moon. This gave them a unique perspective of our natural satellite. Nowadays, spacecraft continue to study the far side. And in 2019, China's Chang'e -4 mission became the first to land a rover on the far side, making new discoveries about the surface and geology. So, While the dark side of the moon is a catchy phrase, it's a bit misleading. Both sides of the moon experience daylight and night, and the far side remains just as much a part of the moon as the side we always see. It's simply the part we never get to observe from Earth, which is why it's often shrouded in mystery. The moon always shows the same face to Earth because of something called synchronous rotation. This means that the moon takes the same amount of time to rotate once on its axis as it does to orbit Earth. In simple terms, the moon's day is as long as its year. This is why we always see one side of the moon while the other side stays hidden from view. The moon's rotation and orbit are closely linked in a way that has developed over millions of years. When the moon first formed, it likely rotated much faster. But over time, Earth's gravity slowed down the moon's rotation. This is a process called tidal locking. The gravitational pull from Earth created tidal forces on the moon, which gradually slowed down its spin until it matched the time it took to orbit Earth. This is why the same side of the moon faces us today. To picture this, think about spinning a basketball on your finger. If you were to walk around the ball, you would see all sides of it. But if you spin the ball in such a way that you always keep the same part of it facing you, you're mimicking what the moon does. As the moon orbits Earth, its rotation is synchronized with its orbit, so only one side of the moon is ever visible from Earth. This synchronized movement means that the moon's near side, the side we see, is always facing us, while the far side remains hidden. Even though both sides of the moon experience day and night, we never get to see the far side from Earth. This has to do with the moon's slow rotation, which happens in perfect sync with its orbit around our planet. Synchronous rotation, many moons around other planets in the solar system also show this behavior, meaning they always present the same side to their parent planet. It's a result of the same tidal forces that Earth's gravity has exerted on the moon. Over time, these forces lead to a situation where the moon's rotation becomes locked in with its orbit. The moon's synchronous rotation also has another effect on Earth. It stabilizes our planet's rotation. Without the moon, Earth's tilt would be more unstable, which could cause extreme changes in our climate over long periods. The moon helps keep Earth's tilt more stable, providing a relatively steady climate over thousands of years. The process of synchronous rotation took millions of years to happen. It's believed that when the moon first formed, it didn't show this behavior. The moon may have been rotating much faster at that time, but the tidal forces from Earth acted like a brake on the moon's spin, gradually slowing it down over time. Eventually, the moon reached the point where its rotation period matched its orbit, locking the same side toward Earth. This steady, predictable motion has been in place for billions of years. The moon's synchronous rotation is a result of these gravitational interactions and shows how forces from one body can affect the rotation of another. Even though we can't see the far side of the moon from Earth, spacecraft and missions have been able to study it. The far side has become an area of interest for exploration, as it offers a unique perspective on the moon's history and surface. The moon experiences quakes, known as moonquakes, similar to the earthquakes we feel on Earth. These moonquakes happen for different reasons, such as tidal forces, impacts from meteoroids, and stresses within the moon's interior. One of the main causes of moonquakes is tidal forces. Just as Earth's gravity causes the oceans to rise and fall, the moon's gravity causes a similar effect on Earth, known as the tides. But the moon also feels these tidal forces from Earth. As Earth's gravity pulls on the moon, it causes slight stretching and squeezing within the moon's crust. These forces create stress inside the moon, leading to moonquakes. The moon's crust is not as flexible as Earth's, so when it is stretched, the energy often causes the ground to shake. These tidal forces are a constant source of moonquakes. although they tend to be small and not very strong. Moonquakes can also happen when meteoroids strike the moon's surface. The moon doesn't have an atmosphere to protect it from objects traveling through space. When meteoroids hit the surface, the impact can release a lot of energy, shaking the ground. These quakes can vary in size, depending on the size of the meteoroid and the force of the impact. While these types of moonquakes are often short-lived, they can sometimes be more powerful than those caused by tidal forces. Another type of moonquake comes from internal stresses within the moon. These quakes are caused by changes in the moon's interior, possibly due to cooling or shifting of materials deep beneath the surface. The moon is not entirely solid. Parts of its interior are still somewhat molten. As the moon cools over billions of years, it may experience shifts in its internal structure. These shifts can cause the crust to crack or adjust, leading to a quake. While these quakes are not as frequent, they can be more intense than others. Interestingly, some moonquakes are strong enough to be detected by sensitive equipment, even though they're not powerful enough to cause damage like earthquakes do on Earth. The Apollo missions set up seismometers on the moon's surface to measure these moonquakes. These devices recorded thousands of moonquakes during the missions. Some were quite weak, but others were stronger and lasted longer, giving scientists valuable information about the moon's internal structure. Moonquakes are also important for understanding the moon's geologic history. By studying these quakes, scientists can learn more about how the moon formed and how its interior has evolved over time. The fact that the moon still experiences quakes, despite being much smaller and geologically less active than Earth, shows that there are still processes taking place inside it. While moonquakes are a fascinating phenomenon, they're not a major hazard for astronauts. The Apollo missions experienced only minor shaking from moonquakes, and there's no evidence that they would cause significant damage to structures on the moon, at least in the way earthquakes can cause destruction on Earth. However, understanding moonquakes is important for future missions, especially as humans plan to return to the moon and establish long-term bases. Knowing how moonquakes might affect buildings or equipment will help ensure that astronauts are safe and that the structures they build can withstand the quakes. In a way, moonquakes provide us with a window into the ongoing processes that are still shaping the moon today. They show us that even though the moon may seem quiet, it is still an active and dynamic place. The moon's surface is covered with over 500,000 craters. These craters were created by collisions with meteoroids, asteroids, and comets that have hit the moon over billions of years. Unlike Earth, the moon has no atmosphere to protect it, so it is constantly bombarded by space debris. When a meteoroid or asteroid crashes into the moon, it releases a huge amount of energy. This impact causes the surface to crack and form a crater. The size of the crater depends on the size and speed of the object that hits the moon. Smaller impacts create smaller craters, while larger objects can create massive craters, some of which are hundreds of kilometers wide. Many of the moon's craters were formed early in its history, during a period known as the Late Heavy Bombardment. This was a time when the solar system was still young, and there were many more objects floating around in space. As these objects collided with the moon, they left behind scars that have lasted for billions of years. Unlike Earth, the moon doesn't have weather or tectonic activity to erase these craters, so they remain intact. Some of the largest craters on the moon are very old and date back to the beginning of the solar system. For example, the South Pole, Aitken Basin, is one of the largest and oldest impact craters on the moon. It's about 2,500 kilometers in diameter and over 13 kilometers deep. These large craters give scientists clues about the moon's early history and the types of objects that were around during the solar system's formation. Smaller craters are also common on the moon, and they range from tiny pits to medium-sized craters that can be seen with a telescope. These craters are formed by smaller meteoroids or fragments of asteroids. Since the Moon lacks an atmosphere, these smaller objects can strike the surface at very high speeds, creating craters that are often sharp, edged, and well-defined. Over time, the Moon's craters have been affected by other forces. Some of the older craters have been worn down by the effects of space weather, like solar radiation and micrometeorite impacts. However, because the Moon lacks the processes like wind and water erosion that we have on Earth, these craters last for a much longer time. Some of the craters still retain the bright rays of material that were ejected during the impacts, which can be seen as streaks radiating out from the crater. Many of the craters on the Moon also contain important geological features. Some craters are filled with dark, flat plains of solidified lava, which were formed by volcanic activity on the Moon billions of years ago. These plains, called maria, make up about 16% of the Moon's surface and are mostly found on the side facing Earth. The rest of the Moon's surface is covered by lighter, more cratered highlands. The presence of so many craters on the Moon is also useful for scientists studying the history of the solar system. Each crater provides a record of when and how objects collided with the Moon. By studying the sizes and distribution of craters, scientists can learn more about the timing of the impacts and how the Moon's surface has changed over time. The craters on the Moon also tell us about the Moon's relationship with Earth. Some of the craters are relatively young, having formed during periods of intense meteorite bombardment. Others are much older, dating back to when the Moon first formed. The study of these craters helps scientists understand the processes that shaped not only the Moon but also the Earth and other planets in the solar system. In the future, the craters on the Moon may become even more important. As humans return to the Moon for exploration and possibly colonization, the craters could serve as natural resources. Some of the craters are thought to contain water ice, which could be used for drinking water or fuel. Scientists are also interested in studying the craters to learn more about the Moon's history and its potential for future exploration. In 2009, NASA confirmed the presence of water ice on the Moon. This discovery was significant because it suggested that the Moon, which was once thought to be completely dry, actually has water, especially in areas that are permanently shadowed. These areas are mostly found at the Moon's poles, where sunlight never reaches. The key to finding this water lies in the Moon's polar region. Unlike the rest of the Moon, which experiences long periods of daylight and darkness due to its rotation, the poles have craters that are always in shadow. These craters, known as permanently shadowed regions, are cold enough to trap water ice for billions of years, even though the Moon's surface can get extremely hot during the day and very cold at night. The temperatures in these shadowed craters stay low enough to keep the water ice stable. NASA's discovery came after years of research and space missions aimed at understanding the Moon's resources. The presence of water ice was detected using instruments on spacecraft such as the Lunar Reconnaissance Orbiter and the Lunar Crater Observation and Sensing Satellite LELCROSS. These missions sent signals or dust plumes to study the composition of the Moon's surface, which revealed traces of water ice hidden in the deep shadowed craters. This discovery is important for future lunar exploration. Water is a vital resource for human life, and having access to water on the Moon could make long-term stays there much more feasible. Astronauts would be able to use this water for drinking, but it could also be split into hydrogen and oxygen for fuel. This would make it possible to produce oxygen for breathing and hydrogen for rocket fuel, potentially reducing the need to transport these resources from Earth. The water ice on the Moon is not easy to access. It is buried in the cold, shadowed craters, and getting to it would require specialized equipment. However, scientists are optimistic that with the right technology, this ice could be extracted. In fact, the presence of water on the Moon could play a key role in future missions, such as NASA's Artemis program, which aims to send astronauts back to the Moon and establish a sustainable human presence there. The discovery of water ice on the moon also opens up new questions about the moon's history. How did the water get there? One theory is that water may have been brought to the moon by comets that collided with it in the past. Another theory suggests that solar wind could have contributed to the formation of water molecules on the moon's surface. The truth is still unclear, but the presence of water on the moon gives scientists a new area to explore in their quest to understand the moon's formation and evolution. This discovery also has broader implications for our understanding of the solar system. Water is essential for life as we know it, and finding it on the moon could provide insight into the possibility of water and life on other planets and moons in the solar system. It's also a step forward in preparing for the exploration of Mars and other distant worlds where having access to water will be just as important. In the years since NASA's discovery, there have been additional missions and plans to further study the moon's water resources. The presence of water ice on the moon makes the idea of using the moon as a base for space exploration more realistic. It also gives scientists and engineers a new challenge: how to safely and efficiently access and use that water for future missions. As we learn more about the moon's water, we also gain a better understanding of how to explore and utilize resources in space. The moon has a very thin atmosphere called an exosphere. Unlike Earth's thick atmosphere, which is made up of oxygen, nitrogen, and other gases that support life and weather, the moon's exosphere is made up of just a few light gases, including helium, neon, and hydrogen. This exosphere is extremely thin and cannot support life or create weather as we know it. The gases in the moon's exosphere are so sparse that they don't behave like the air we breathe. Instead of forming a dense layer around the moon, the particles in the exosphere are spread far apart. This makes the moon's atmosphere very different from Earth's, where air molecules are tightly packed and able to interact with each other to create things like wind and clouds. The exosphere doesn't have enough particles to cause significant pressure, which means it can't trap heat the way Earth's atmosphere does. As a result, during the day, when the sun is shining on the surface, the temperature can soar to over 100 degrees Celsius. At night, without an atmosphere to hold the heat, the temperature can plummet to around negative 170 degrees Celsius. The moon's exosphere is also unable to protect the surface from harmful radiation from the sun. Earth's atmosphere acts as a shield, blocking much of the sun's harmful rays. But on the moon, there is no such protection. This lack of atmosphere contributes to the harsh environment on the moon's surface, where temperatures can fluctuate wildly, and the surface is constantly bombarded by solar radiation and micrometeorites. The gases in the moon's exosphere are not there in large amounts. They exist in extremely low concentrations and are constantly being lost to space. Some of these particles may come from the solar wind, which is a stream of charged particles emitted by the sun. The solar wind can knock atoms off the moon's surface and into the exosphere. However, because the exosphere is so thin, these particles don't stay there for long and are gradually lost to space. Because of the exosphere's thinness, the moon does not have the conditions needed to support life. Without a thick atmosphere to provide oxygen, protect from radiation, and regulate temperature, the moon is not a hospitable environment for living organisms. This makes the moon a harsh and barren place, with no air to breathe or weather to experience. However, the moon's exosphere is still an area of interest for scientists. By studying it, researchers can learn more about the behavior of atmospheres in space. The exosphere on the moon is a unique example of a very thin atmosphere, and understanding how gases behave in such an environment could provide insights into the atmospheres of other celestial bodies, such as Mercury or Mars. In future missions to the moon, scientists will continue to study the exosphere to better understand its composition and how it affects the moon's surface. They will also explore ways to protect astronauts from the harsh conditions caused by the lack of atmosphere, such as radiation and extreme temperatures. But for now, the Moon's exosphere remains a faint, barely, their layer that doesn't provide the conditions needed for life to thrive. The Moon doesn't have a global magnetic field like Earth does. Earth's magnetic field is strong and protects us from solar radiation. But the Moon's magnetic field is much weaker and only exists in certain areas on the surface. These localized magnetic fields suggest that the Moon once had a global magnetic field, which may have disappeared over time. Scientists believe the Moon's magnetic field could have been similar to Earth's early on, but it gradually weakened. The evidence of this ancient magnetic field comes from the Moon's rocks, particularly the ones brought back by the Apollo missions. These rocks show signs of having been magnetized, indicating that they were once exposed to a strong magnetic field. The localized magnetic fields found on the Moon are concentrated in certain regions, especially in the lunar highlands. These magnetic anomalies are not uniform, meaning they are scattered across the surface rather than forming a consistent global field. The strength of these fields is much weaker than Earth's, but they are strong enough to be detected by spacecraft that have orbited the Moon. One possible reason for the Moon's ancient magnetic field is that it had a molten core when it first formed. Early in its history, the Moon might have had a geologically active core, similar to Earth's, which generated a magnetic field through the process of dynamo action. This dynamo effect occurs when the motion of molten metal inside a planet generates a magnetic field. Over time, as the Moon cooled, its core solidified and the dynamo effect stopped, leading to the loss of its global magnetic field. Today, the Moon's lack of a global magnetic field means that it does not have the same protection from the Sunday's solar wind that Earth enjoys. The solar wind is a constant stream of charged particles emitted on Earth. The magnetic field acts as a shield, deflecting these particles away from the surface. Without this protection, the solar wind can interact directly with the Moon's surface, contributing to its erosion and causing changes in its composition over time. This is also why the Moon's surface is constantly exposed to radiation, which makes it an inhospitable place for life as we know it. The presence of localized magnetic fields on the Moon raises interesting questions about its history. Why are these fields found in specific regions? And what do they tell us about the Moon's past? One theory is that these magnetic anomalies are remnants of an ancient magnetic field that was stronger in the past. As the Moon's core cooled, these magnetic regions might have been frozen in the rocks, preserving a record of the Moon's magnetic history. These magnetic fields are also important for understanding the Moon's interaction with the solar wind. In some regions of the Moon, the solar wind is partially deflected by these magnetic fields, creating areas where the surface is less affected by the solar wind. Scientists study these regions to learn more about how the Moon's magnetic field might have protected it in the past, and how it interacts with the solar wind today. The Moon's localized magnetic fields are a fascinating reminder that the Moon has a complex and dynamic history. While it no longer has a global magnetic field, these pockets of magnetism provide valuable clues about the Moon's early years and its geological evolution. Studying these magnetic anomalies helps scientists piece together the story of the Moon's formation and its transformation into the lifeless world we see today. Temperatures on the Moon can change drastically, creating extreme conditions that make it a challenging environment. Since the Moon has no atmosphere to trap heat or distribute temperature, it experiences sharp contrasts between day and night. During the day, when the Sunday shines directly on the surface, temperatures can reach as high as 127 degrees Celsius. At night, when the Sunday is no longer illuminating the surface, the temperature can drop to -173 degrees Celsius. The reason for such extreme temperature differences lies in the Moon's lack of atmosphere. On Earth, our atmosphere helps to regulate temperatures by holding in heat during the night and distributing it during the day. This keeps our planet's temperatures relatively stable. The moon, however, has no atmosphere to buffer these shifts. When the Sunday rises, the surface heats up quickly, reaching scorching temperatures. But when the Sunday sets, the lack of atmosphere means there is nothing to keep the heat from escaping into space, causing the temperature to plummet sharply. During the lunar day, the Sunday's heat directly strikes the surface, warming it up to extreme levels. In contrast, at night, the moon's surface cools rapidly. With no air or water to hold any heat, the temperature drops quickly and deeply. These temperature swings are one of the most noticeable features of the moon's environment, and they present significant challenges for missions to the moon. For example, if astronauts were to spend time on the moon, they would have to be prepared for these temperature extremes. The heat during the day could easily destroy equipment and make it dangerous for humans. At night, the cold could freeze unprotected equipment and pose serious risks to survival. For long-term exploration, this means that astronauts would need to be housed in specially designed habitats that can handle these temperature fluctuations, keeping them warm during the night and cool during the day. The temperature extremes on the moon also affect its surface. The lack of weathering processes, such as wind or rain, means that features on the moon's surface remain largely unchanged. However, the extreme heat and cold can cause the surface material to expand and contract, slowly wearing it down over time. This is why the moon's surface is covered with dust and fine particles known as regolith, which are created by the constant freezing and thawing of surface materials due to the temperature swings. These temperature extremes also impact the moon's potential for future human exploration. The challenges of dealing with such high and low temperatures must be carefully considered when planning missions. For instance, if astronauts were to stay on the moon for extended periods, they would need to store food, water, and equipment in ways that prevent them from being damaged by the temperature shifts. The moon's temperature extremes are one of the main reasons it is a harsh and uninhabitable place. The lack of atmosphere means there is no protection from the Sunday's rays or the cold of space. This creates a difficult environment for any form of life to survive. However, these extreme conditions also make the moon a place of scientific interest. Understanding how materials behave under such temperatures can help scientists learn more about how other celestial bodies, like Mercury or Mars, experience similar conditions. A lunar eclipse occurs when Earth comes directly between the Sunday and the moon, blocking the Sunday's light from reaching the moon. As Earth casts its shadow on the moon can take on a reddish color, which is one of the most striking features of a lunar eclipse. This happens because of a phenomenon in Earth's atmosphere. When sunlight passes through Earth's atmosphere, the light is scattered by the gases and particles in the air. Shorter wavelengths of light, like blue, are scattered more easily, while longer wavelengths, like red, pass through the atmosphere more directly. The red light that survives this scattering process is bent or refracted around Earth and then shines onto the moon. This is why the moon takes on a reddish hue during a lunar eclipse, often referred to as a blood moon. The key to the red color is the way Earth's atmosphere filters sunlight. Even though the Sunday's light is mostly white, it's made up of many different colors of light. When sunlight travels through Earth's atmosphere, the shorter, bluer wavelengths are scattered in all directions, leaving the longer, redder wavelengths to pass through and reach the moon. This gives the moon its reddish glow during the eclipse. The moon doesn't disappear completely during a lunar eclipse, as some might expect. Instead, it remains visible, but takes on a dim, eerie red color. This occurs because of the Earth's atmosphere bending sunlight toward the moon, despite the fact that the Sunday's direct light is blocked by Earth. Lunar eclipses are different from solar eclipses. In a solar eclipse, the moon moves between the Earth and the Sunday, blocking the Sunday's light from reaching Earth. But during a lunar eclipse, It's Earth that casts a shadow on the moon. This is why lunar eclipses are visible from anywhere on Earth where the moon is above the horizon. People across the world can see the eclipse, as long as they have clear skies and the timing is right. A lunar eclipse doesn't happen every month, even though the moon orbits Earth about once every 27 days. This is because the moon's orbit is tilted relative to Earth's orbit around the Sunday. For a lunar eclipse to happen, the Sunday, Earth and Moon need to align in a straight line, which only happens a few times a year. When the alignment is perfect, a lunar eclipse occurs and the shadow of Earth falls on the moon. The red color of the moon during a lunar eclipse has fascinated people for centuries. Ancient cultures often interpreted these events as omens or signs. Today, we know that the red hue is simply the result of the way sunlight interacts with Earth's atmosphere, but the sight of the moon changing color remains a powerful and mysterious event that continues to captivate observers around the world. The moon's soil, called regolith, is quite unique. Unlike Earth's soil, which is made up of organic material, water, and a mix of minerals, lunar soil is a mixture of fine dust particles, minerals, and rocks. It forms over billions of years due to constant bombardment by meteoroids, asteroids, and solar radiation. Regolith is made up of tiny fragments of rock that have been shattered by impacts from space debris. When meteoroids crash into the moon's surface, the energy from these impacts breaks the rocks into smaller pieces, which then become part of the regolith. This process of fragmentation happens over and over again, which is why lunar soil is a fine powder that can easily stick to everything, including spacecraft and astronaut suits. One of the most notable features of lunar soil is how it has been altered by the Sunday's solar radiation. The moon doesn't have an atmosphere to protect it from solar winds or cosmic rays, so the soil has been continuously bombarded by these particles. This exposure causes the minerals in the regolith to undergo changes. Over time, the sunlight and radiation break down the surface materials, leading to the formation of tiny rounded beads called solar wind-implanted particles. These particles are rich in hydrogen and helium, which are carried by the solar wind. This constant bombardment also makes the lunar soil chemically different from Earth's soil, with little to no water content. The regolith is also composed of a variety of minerals, including silicates, like plagioclase, pyroxenes, and olivine. These minerals form as the result of volcanic activity that occurred on the moon billions of years ago, when lava flowed across its surface. These volcanic rocks are now scattered across the moon's surface, embedded in the regolith. Some areas of the moon's surface have a higher concentration of certain minerals, which can vary based on their location. For example, the darker areas of the moon, known as the Maria, contain more basalt, a type of volcanic rock, while the brighter highland regions are rich in feldspar and other minerals. Lunar soil also has a very low level of moisture. Unlike Earth, where soil contains water and organic materials that support plant life, lunar soil is completely dry. This makes the moon a challenging place for growing crops or sustaining life without significant technological help. The lack of moisture also means the moon's regolith doesn't undergo the same weathering processes that Earth's soil does. On Earth, rain, wind, and plant roots constantly alter and mix the soil. On the moon, though, the regolith has remained largely unchanged for billions of years. The composition of lunar soil makes it a valuable resource for future exploration. Scientists believe that regolith could potentially be used to create oxygen, water, and even building materials for a lunar base. One idea is to extract oxygen from the minerals in the regolith by heating it up, or using chemical processes. The fine dust in lunar soil, however, is a challenge for astronauts. It can get into equipment and spacesuits, causing damage or discomfort. The dust particles are extremely sharp and cling to everything, which makes it difficult to work in the moon's environment. Lunar soil's unique properties provide important insights into the moon's history. The impacts from meteoroids, the absence of weathering, and the effects of solar radiation all contribute to the moon's surface being a preserved record of the solar system's past. The regolith can tell scientists about the conditions on the moon over billions of years, including how it was affected by impacts and the solar wind. By studying lunar soil, scientists gain a better understanding of the moon's geological history and how it has evolved. As plans for lunar exploration continue, regolith will likely become an even more important resource. The unique nature of the moon's soil makes it a potential asset for astronauts working on the moon in the future. However, understanding how to use it effectively and deal with its challenges is key to successful long-term missions. The moon plays a major role in causing ocean tides on Earth. Its gravity pulls on Earth's oceans, creating a regular rise and fall of water levels along coastlines. These tides are not just an interesting natural phenomenon. They have a big impact on coastal patterns, ecosystems, and even human activities. When the moon's gravity pulls on Earth, it creates a bulge in the water closest to it. This is what we call the high tide. At the same time, there is another bulge on the opposite side of Earth. This happens because Earth itself is also pulled slightly toward the moon, but the water on the far side isn't affected in the same way, creating a second high tide. Between these two high tides, the water level drops, creating the low tide. As the Earth rotates, different places move in and out of these bulges, causing the tides to rise and fall at regular intervals. The strength of the tides depends on several factors, including the alignment of the Earth, Moon, and Sunday. When the Sunday, Moon, and Earth line up, the tidal effect is stronger, creating what's known as a spring tide. This doesn't have anything to do with the season of spring. It's just a term used to describe when the tides are at their highest. When the Sunday and Moon are at right angles to each other, the tides are weaker, and these are called neap tides. The Moon's influence on tides affects more than just the water level. The rise and fall of the tides can shape the coastline over long periods, creating features like tidal flats, beaches, and estuaries. As the tide goes in and out, it moves sediment around, helping to build and reshape the landscape. Coastal ecosystems, including salt marshes, mangroves, and mudflats, rely on the tides to bring in nutrients and support plant and animal life. Tidal patterns play an important role in the lives of many marine species, influencing when they feed, breed, and migrate. Tides are also important for human activities. For example, tidal patterns affect fishing, as certain species are more likely to be found during specific tidal conditions. Coastal communities depend on tides for things like navigation, as high tides can help boats reach ports, while low tides might expose hazards like rocks or sandbars. Tidal power, a form of renewable energy, is also harnessed in some places to generate electricity from the movement of water. In addition to affecting the tides, the moon also plays a role in stabilizing Earth's axial tilt. This helps maintain a stable climate over long periods, which is crucial for life on Earth. Without the moon's gravitational pull, Earth's tilt could shift more dramatically, leading to more extreme changes in climate, while the moon's pull on Earth's oceans is responsible for the tides. It also has a slower effect on Earth over time. The moon's gravity gradually slows down Earth's rotation. This effect has been happening for billions of years, and as a result, a day on Earth is getting longer. In the past, Earth's days were much shorter, but over time, the moon's pull has lengthened them. The moon is also slowly moving away from Earth, at a rate of about 3.8 centimeters per year. The moon's influence on Earth's tides is one of the most noticeable ways in which the moon affects life on our planet. It shapes the coastlines, supports ecosystems, and even impacts human activities. Without the moon's gravitational pull, Earth would have very different tides, and our planet's environment would be much less stable. The moon's pull on the oceans is just one example of how this distant satellite continues to have a profound impact on life here on Earth. Lunar dust is one of the most challenging aspects of the moon's environment. During the Apollo missions, astronauts discovered that the dust on the moon is sharp, abrasive, and incredibly clingy. It's made up of tiny, jagged particles of rock that have been ground down by constant meteoroid impacts over billions of years. These particles are so fine that they can get into every crevice, making them a serious hazard for both astronauts and equipment. One of the most notable characteristics of lunar dust is how easily it sticks to surfaces. Because there's no atmosphere to blow the dust away, it clings to everything it touches. The tiny dust particles have electrostatic charges, which means they are attracted to objects and can stick even in low-gravity environments. During the Apollo missions, astronauts had a hard time keeping their spacesuits, equipment, and even their spacecraft clean. Lunar dust stuck to their suits and gear, making it difficult to remove. The sharp nature of the dust also poses risks. Since the particles are jagged and hard, they can scratch and damage delicate equipment. For example, the dust could potentially damage camera lenses, solar panels, and other instruments. The abrasive quality of the dust can also wear out equipment more quickly, leading to the need for frequent maintenance or replacement. For astronauts, lunar dust could be even more dangerous. The fine particles can easily get into the airlock or inside spacesuits. If inhaled, lunar dust could irritate the lungs and pose a health risk. Similar to how fine dust or asbestos can be harmful on Earth, the Apollo astronauts had to be very careful not to bring the dust inside the lunar module, as it could get into the air supply or even interfere with the equipment inside. The dust also presents challenges for long-term exploration of the moon. Any future lunar bases or missions will need to account for how to deal with lunar dust. Developing ways to clean equipment and spacesuits, or even preventing the dust from sticking in the first place, will be essential. Scientists are working on creating materials and technologies that can either repel lunar dust or make it easier to remove, which will be important for future missions, especially if astronauts are living and working on the moon for extended periods. Lunar dust also affects the moon's surface. Over time, it builds up and can change the surface's texture, giving it a layer of fine powdery material. This regolith, made up of dust and small rocks, covers the entire surface of the moon. While this dust may look soft, it's a tough and abrasive layer that can make it difficult for future exploration vehicles to move smoothly across the surface. The challenge of lunar dust is something scientists are keen to understand better, studying how it behaves, how it affects equipment, and how to mitigate its impact will be key to ensuring that future missions to the moon are successful and that astronauts stay safe. Until we find effective solutions, lunar dust will remain a tricky problem, making it one of the many unique challenges that come with exploring the moon. The moon's light isn't its own, it actually reflects the light of the Sunday. While it may appear bright in the night sky, the moon doesn't generate its own light like a star does. Instead, the Sunday's rays shine on the moon's surface, and the moon reflects that light back to Earth. This reflection is what makes the moon so visible and bright at night. The moon's surface is covered in dust and rocky material that reflect sunlight. Some areas, like the darker regions called Maria, reflect less light, while the lighter areas, known as the highlands, reflect more. However, even the areas that appear darker to us still reflect a good amount of sunlight. In fact, the moon reflects about 12% of the sunlight that hits it, which is why it can be so bright compared to stars or other celestial bodies in the night sky. When sunlight hits the moon, it bounces off the surface and travels to Earth. This reflection can vary depending on the moon's position in its orbit. When the moon is full, it is fully illuminated by the Sunday, and its reflection is at its brightest. When it's in a new moon phase, we can't see the moon because it is between the Earth and the Sunday, and the side of the moon that faces Earth is in shadow. The light that we see from the moon is also affected by the Earth's atmosphere. As the light passes through the atmosphere, it can scatter, which is why the moon can sometimes appear yellow or red, especially during certain phases or lunar events. But no matter the color, the light we see from the moon is always sunlight that has been reflected off its surface. The moon's ability to reflect light has been important throughout history. Before artificial lighting, the moon's light was a significant source of illumination at night. Ancient civilizations often based their calendars and timekeeping on the phases of the moon, using its light as a natural guide. Even today, the moon's glow helps light up the night sky and guide travelers. In summary, the moon shines brightly at night because it reflects sunlight. It doesn't create light on its own, but its surface is good at bouncing sunlight back to Earth, making it one of the most prominent features in the night sky. The moon's orbit around Earth is not a perfect circle. It's elliptical. This means that the distance between the moon and Earth changes as the moon travels along its orbit. The closest point in the moon's orbit to Earth is called perigee, and the farthest point is called apogee. At perigee, the moon is about 356,500 kilometers away from Earth. This is when it appears slightly larger and brighter in the sky, which is often referred to as a supermoon. The increased size and brightness happen because the moon is closer to Earth, and its light doesn't have to travel as far to reach us. On the other hand, at apogee, the moon is about 406,700 kilometers away from Earth. During this time, the moon appears smaller in the sky, often referred to as a micromoon. The difference in size between a supermoon and a micromoon isn't huge, but it can be noticeable, especially when the moon is near the horizon. The elliptical orbit also causes variations in the moon's gravitational pull on Earth, which can affect tides. When the moon is at perigee, its gravitational pull on Earth is stronger, leading to higher tides. At apogee, the pull is weaker, resulting in lower tides. These changes in tidal strength happen over the course of the moon's orbit, which takes about 27.3 days. This elliptical orbit is a natural part of how the moon moves around Earth. It's caused by the gravitational forces between Earth and the moon, as well as the influence of other objects in the solar system. Even though the orbit is elliptical, the distance between the Earth and moon doesn't vary wildly. It changes in a smooth, regular cycle. The variation in the moon's distance from Earth also plays a role in understanding how the Earth-Moon system works. Over time, the moon is gradually moving away from Earth, but the changes in its orbit from perigee to apogee are still relatively small on a daily basis. These subtle differences have helped scientists learn more about the gravitational interactions between Earth and the moon. The surface of the moon is mostly dry, with no liquid water or large bodies of water. Even though scientists discovered water ice at the poles, especially in permanently shadowed craters, the moon's surface as a whole is extremely dry. There are no lakes, rivers, or oceans like we have on Earth. The lack of liquid water is one of the main reasons the moon is such a harsh and inhospitable place. Without liquid water, the moon cannot support life as we know it. The surface is covered in a layer of fine, dry dust called regolith, which has been formed over billions of years by constant meteoroid impacts. This regolith is made up of small fragments of rock and mineral grains that have been shattered and ground down, but it contains no water in a form that could sustain life. While the discovery of water ice in the shadowed regions at the moon's poles is significant, this ice is trapped in extremely cold environments and isn't accessible in liquid form. The temperature in these permanently shadowed craters can be as low as -250 degrees Celsius, far colder than anything we experience on Earth. So, Even though this ice might be useful for future lunar missions, it isn't available in the way liquid water is on Earth. In the areas where sunlight shines, the surface temperature can get so hot, up to 127 degrees Celsius during the day, that any water present would quickly vaporize. At night, when the moon's surface cools, temperatures can plummet to minus 173 degrees Celsius, so any water would freeze almost immediately. This constant cycle of extreme heat and cold makes it impossible for liquid water to remain on the moon's surface. Scientists believe the moon may have had water in its past, but over billions of years it was lost due to the lack of atmosphere. Without an atmosphere to trap gases and hold on to water, it would have been difficult for any liquid to stay on the surface, especially with the moon's small size and weak gravity. Water molecules may have been broken apart by solar radiation, and any hydrogen and oxygen would have escaped into space over time. In summary, despite the discovery of water ice at the poles, the moon's surface is largely dry. There is no liquid water, and no large bodies of water exist anywhere on the moon. The lack of water and an atmosphere makes it a very different environment from Earth, making it a challenging place for human exploration and life. On the 20th of July, 1969, Neil Armstrong and Buzz Aldrin made history as the first humans to walk on the moon. They were part of NASA's Apollo 11 mission, which marked a major achievement in space exploration. This event was not only a triumph for science and technology, but also a moment of wonder for people all around the world. The journey began a few days earlier, when the Apollo 11 spacecraft launched from Earth, carrying Armstrong, Aldrin, and their colleague Michael Collins. Armstrong and Aldrin would land on the moon, while Collins remained in orbit around it in the command module. The trip to the moon took about 4 days, and during that time, the astronauts made final preparations for the lunar landing. When they reached the moon, the lunar module, called the Eagle, separated from the command module and began its descent to the surface. The landing was not easy. Armstrong had to manually pilot the spacecraft through an unexpected rocky area. As they approached the surface, the computer's automated landing system wasn't able to detect the terrain well enough to guide the spacecraft safely. Armstrong took control, guiding the Eagle to a smooth landing with just seconds to spare. When they finally touched down, Armstrong famously spoke the words, "Houston, Tranquility Base here. The Eagle has landed." After making sure everything was stable, Armstrong stepped out of the lunar module and became the first person to set foot on the moon. His first words as he stepped onto the surface were, "That's one small step for a man, one giant leap for mankind." These words have since become iconic, symbolizing the incredible achievement of humanity reaching another world. Aldrin followed shortly after, joining Armstrong on the moon's surface. Together, they spent about 2 hours walking on the moon, collecting rocks, setting up experiments, and taking photographs. The surface of the moon was a strange and barren place. The astronauts wore heavy spacesuits, which were necessary to protect them from the harsh conditions, such as the lack of atmosphere and the extreme temperatures. Despite the weight of their suits and the low gravity on the moon, which is about 1/6 of Earth's, Armstrong and Aldrin were able to move around with relative ease, though they looked almost as if they were bouncing with every step. One of their key tasks was to collect samples of lunar soil and rocks. They used a tool called a sample collection bag to gather material from the surface. These samples would later provide important scientific data about the moon's composition and help scientists learn more about its history. In addition to collecting samples, the astronauts set up a few scientific instruments, including a seismometer to measure moonquakes and a laser reflector that would help scientists on Earth measure the distance to the moon with great accuracy. While on the moon, Armstrong and Aldrin also planted the American flag, which fluttered slightly due to the lack of wind. The flag's placement was a symbolic moment, representing humanity's ability to reach beyond Earth and touch another world. They also took time to enjoy the silence of the lunar landscape, with the only sounds coming from their own breathing and the radio communications with mission control back on Earth. The moonwalk lasted a total of about 21 hours, but the astronauts' time on the moon itself was short, about 2.5 hours. After completing their tasks, they returned to the lunar module, where they joined Collins, who had remained in orbit. The three astronauts then began their journey back to Earth, where they were greeted as heroes. Armstrong and Aldrin's walk on the moon marked a turning point in human history. It was the first time humans had left Earth and set foot on another celestial body. Their success was the result of years of planning, hard work, and innovation, and it demonstrated humanity's potential to achieve incredible feats in space exploration. While their footsteps on the moon were small, their impact has lasted for generations. The moon is eerily silent because it has no atmosphere. On Earth, we hear sounds because air carries sound waves. Sound waves are vibrations that travel through a medium, like air, water, or even solid objects. But on the moon, there's no air or any other substance to carry these waves. So sound cannot travel. This makes the moon a quiet place, devoid of the usual sounds we experience on Earth. If you were standing on the moon, you wouldn't hear anything, even though you might see people talking or equipment moving. In fact, the only sounds an astronaut would hear would be through their helmet and spacesuit. These suits are designed to keep astronauts alive in the harsh conditions, and part of their design includes a communications system. This system allows astronauts to hear each other and communicate with mission control on Earth. But all of it is transmitted through the suit's internal equipment, not the air around them. Without the atmosphere to carry sound waves, the sounds of the world would be completely absent. This lack of sound is a direct result of the moon's environment. Earth's atmosphere is made up of gases like nitrogen and oxygen, which allow sound to travel. These gases vibrate when sound waves pass through them, and our ears pick up those vibrations, which we interpret as sound. The moon, however, has no atmosphere to vibrate. Its surface is exposed directly to space, with no air to carry the sounds we take for granted on Earth. Because of this, sound waves simply do not travel on the moon. In some ways, the silence is an unsettling feature for astronauts. During the Apollo missions, when astronauts stepped onto the moon, the lack of sound was striking. They could hear the muffled noise of their own movements inside their spacesuit. But outside, everything was silent. The only sounds that could reach them were the vibrations of their own equipment, like the movements of their lunar module or their spacesuit's life support systems. Everything else, whether it was a rock being dropped or a hammer being struck, was silent. This absence of sound has been a useful fact for scientists too. On Earth, sounds can interfere with sensitive equipment. In space, the silence of the moon allows scientists to study its surface and environment without the complications that sound could introduce. The lack of sound on the moon also means that things like explosions or impacts from meteorites would be silent, unless they were recorded by instruments like those that measure seismic activity. The silence on the moon stands in stark contrast to Earth, where sounds are part of everyday life. On Earth, sound creates a constant background noise, from the wind blowing through trees to the hum of machinery. In space, there's nothing to create or carry those sounds, leaving an overwhelming quiet. Even though we've sent spacecraft to the moon and collected valuable data, the moon remains a place where the usual sensations of sound don't exist. For astronauts working on the moon, this silence requires some adjustment. While they can communicate with each other and with Earth, the absence of external noise is a constant reminder that they are in a completely different environment. Their movement and actions become the source of sound, but these noises are muffled by the design of their suits and equipment. To them, the moon is not just a place without an atmosphere. but also a place where sound, something so essential to life on Earth, doesn't exist. The Moon is much smaller than Earth. In fact, it's about 1/81st of Earth's mass. This means that if you could somehow weigh both the Earth and the Moon, Earth would be 81 times heavier than the Moon. Despite its smaller size, the Moon still has enough mass to exert a noticeable gravitational pull on Earth, which is why we experience tides and why the Moon orbits our planet. The Moon's smaller mass also means it has weaker gravity compared to Earth. On the Moon, gravity is only about 1/6, as strong as it is on Earth. This difference is why astronauts can jump so much higher on the Moon than they can on Earth. They weigh significantly less on the Moon, and the weaker gravity allows them to lift off the ground more easily. The Moon's size also affects its ability to hold onto an atmosphere. Because its mass is so much smaller than Earth's, the Moon has much weaker gravity, which means it can't retain gases the way Earth can. This is why the Moon has no significant atmosphere. Without an atmosphere, there's no air to breathe, and there are no weather systems like those on Earth. The lack of atmosphere also means the Moon cannot support life, as we know it. And there is no protection from the Sun's harmful radiation. The Moon's small mass also impacts its ability to create a magnetic field. Unlike Earth, which has a strong magnetic field that helps protect us from solar radiation, the Moon doesn't have a global magnetic field. Some regions on the Moon do have localized magnetic fields, which may be remnants of an ancient, stronger magnetic field. But overall, the Moon's smaller mass and lack of internal heat have made it unable to maintain a global magnetic field, like Earth's, while the Moon's small size and mass may limit some of its characteristics. They also contribute to the unique relationship it has with Earth. The Moon's lower gravity means that its surface features, such as craters and mountains, don't erode as quickly as they would on Earth. The Moon has experienced little change since its formation billions of years ago, and its surface still bears the marks of countless meteoroid impacts. This smaller mass also affects the Moon's orbit. The Moon orbits Earth in a stable path, but because it's so much lighter than Earth, its movement is influenced more by Earth's gravity. In fact, the Earth's gravity is slowly pulling the Moon away from Earth at a rate of about 3.8 centimeters per year. This is a gradual process, but it's a sign of how the two bodies interact, with Earth's larger mass exerting a strong gravitational influence on the Moon. Though the Moon is much smaller than Earth, its mass is enough to influence our planet in important ways. It's responsible for the tides that shape Earth's coastlines, and its gravity helps stabilize Earth's axial tilt, which in turn stabilizes our climate over long periods. Even though it's 1/81st the size of Earth, the Moon plays a significant role in maintaining the conditions necessary for life on Earth. The Moon doesn't experience the same kind of erosion that Earth does. On Earth, wind, water, and other natural processes constantly reshape the surface, slowly wearing down mountains, valleys, and craters. However, the Moon doesn't have these forces to act on its surface. It lacks an atmosphere to carry wind, and there is no liquid water to cause erosion. As a result, the features on the Moon's surface, such as craters, remained largely unchanged for billions of years. Erosion on Earth happens in many ways. Wind can blow sand across the desert, wearing down rock formations. Water in rivers can carve out deep valleys. On Earth, these forces are active every day, slowly altering the landscape. But on the Moon, without an atmosphere or weather, nothing happens to wear down its surface. The lack of wind means that dust and particles don't get blown around. Without rain or snow, there is no water to erode rocks or fill in craters. This absence of erosion has preserved many of the Moon's features. Craters that were formed billions of years ago by meteorite impacts are still clearly visible today. On Earth, such craters would have been worn away by wind, rain, or the movement of tectonic plates. But on the Moon, These impacts remain unchanged and untouched by weathering forces. The Moon's surface has been bombarded by meteoroids for billions of years, and the craters from these impacts are still there, offering a clear view of the Moon's history. One example of this is the large, dark plains known as the Maria. These plains were created by ancient volcanic activity. They were once filled with molten rock that slowly cooled and solidified. Over time, meteorites continued to impact the surface. But because there was no water or weather to alter the landscape, the Maria have remained largely intact. The same goes for the numerous smaller craters scattered across the Moon's surface. Even though they may have been formed billions of years ago, they still appear as sharp, well-defined features. The lack of erosion on the Moon also means that scientists can study its surface in a way that is not possible on Earth. The Moon's surface acts like a record, preserving the history of impacts, volcanic activity, and other events. Each crater and rock formation provides clues about the Moon's past. Since there is no erosion to erase these features, scientists can examine them to understand the conditions in the solar system billions of years ago. The Moon's surface remains relatively unchanged because of its lack of weathering forces. The absence of an atmosphere means that wind doesn't erode the land, and the lack of liquid water means there is no runoff to reshape the surface. This helps preserve features like craters and mountains, allowing them to last for billions of years. The Moon offers a unique opportunity for scientists to study a surface that has remained relatively unchanged by natural processes, giving us insight into the history of the solar system and the early stages of planetary development. The Moon has ancient lava tubes, which are tunnels created by flowing lava. These lava tubes formed millions of years ago when the Moon's volcanic activity was at its peak. As lava erupted from volcanoes on the Moon's surface, it would flow and cool on the outside, while the molten lava inside would continue to flow, eventually draining away and leaving behind long, hollow tubes or tunnels beneath the surface. These lava tubes are of great interest to scientists and could even play a key role in future lunar exploration. Their structure, which is made of solidified lava rock, is strong and stable. The tunnels could provide shelter and protection from the harsh conditions on the Moon. One of the biggest challenges of living on the Moon is the lack of atmosphere, which means that astronauts would be exposed to extreme temperatures, high levels of radiation, and meteoroid impacts. Lava tubes could offer a natural solution to these problems. The surface of the Moon is constantly bombarded by solar radiation. Without an atmosphere to block these harmful rays, any exposed surface is in danger of being damaged. However, lava tubes are located beneath the Moon's surface, offering a natural shield from radiation. The thick layer of rock surrounding the tubes would act as a barrier, blocking harmful radiation and providing a safe, sheltered space for astronauts. In addition to protection from radiation, lava tubes would also provide shelter from extreme temperature fluctuations. The temperature on the Moon can vary wildly. During the day, when the sun is shining, temperatures can soar to 127 degrees Celsius, while at night they can drop to -173 degrees Celsius. This huge temperature swing makes it difficult to build structures that can handle such extremes. However, lava tubes are naturally insulated. The surrounding rock would help maintain a more stable temperature inside the tubes, providing a much more comfortable environment for astronauts living there. The interior of lava tubes is also protected from the Moon's harsh surface conditions, such as the lack of weathering forces like wind and rain. The interior of these tunnels has remained largely unchanged for billions of years, making them stable and reliable locations for shelter. Some lava tubes on the Moon are large enough to fit entire habitats inside, making them an ideal place for future lunar bases. NASA and other space agencies have been studying lava tubes on the Moon to see how they could be used for human habitation. Some researchers believe that these tubes could be used not just for shelter, but also as locations for research labs, storage areas, and even farming. The idea is that by building habitats inside the lava tubes, astronauts could avoid the extreme conditions on the surface while still being able to live and work on the moon. The tunnels could provide a safe space for long-term missions, reducing the need for heavy shielding or building entirely new structures on the moon's surface. The size of some lava tubes is another reason why they are being considered as potential habitats. Some tubes are wide enough to accommodate multiple buildings or structures. These tubes are long and can extend for kilometers, providing ample space for a variety of activities. If astronauts were to use these tunnels for their base, they would have plenty of room for living quarters, laboratories, and other facilities. Using lava tubes for human habitats would also save time and resources. Instead of having to build entire structures from scratch, astronauts could use the natural features of the moon, which would reduce the amount of construction work required. It would also cut down on the amount of material that would need to be transported from Earth. Since launching materials from Earth is expensive, using natural resources like lava tubes could make lunar exploration more cost-effective. However, before lava tubes can be used for human habitation, scientists and engineers must conduct more research to understand their structure and stability. Some tubes may have collapsed or been damaged over time, and it's important to know which ones are safe for use. Teams would also need to investigate how to transport supplies and build necessary systems inside the tubes, such as power, water, and air systems. The technology to establish such bases is still in development, but lava tubes are a promising option for future lunar missions. Another consideration is how to make the interior of the lava tubes suitable for living. While the tubes provide natural protection from the elements, they would still need to be made livable for humans. Astronauts would need to ensure that the environment inside the tubes is comfortable and functional, which could involve installing life support systems, lighting, and other essential services. The tunnels would also need to be reinforced in certain areas to ensure that they remain safe and secure for long-term habitation. The moon's lava tubes represent an exciting opportunity for lunar exploration. Their natural shelter could offer astronauts a safe and sustainable way to live and work on the moon, especially for long-term missions. By using these tunnels, we could avoid the difficulties of building traditional structures on the moon's surface while benefiting from the natural protection they provide. As we continue to plan for missions to the moon and beyond, lava tubes may play a crucial role in enabling humans to live and thrive in space. The moon takes about 27.3 days to complete one orbit around Earth. This period, known as a sidereal month, is the time it takes for the moon to return to the same position relative to the stars. During this orbit, the moon travels around Earth in an elliptical path, and its distance from Earth changes slightly. But the moon's journey around Earth is not the only factor that affects how we see the moon from our perspective. The movement of Earth itself adds an extra time element. Because Earth is also moving in its orbit around the Sunday, the moon has to travel a bit farther to complete a full cycle from one full moon to the next. This longer period is called a synodic month, and it lasts about 29.5 days. The synodic month is the time it takes for the moon to go from one full moon to the next, which is what we typically refer to when we talk about the moon's phases. Here's how it works. As Earth moves along its orbit, the moon, which is in orbit around Earth, has to travel a little farther to reach the same position relative to the Sunday. This extra distance is what adds those additional 2.2 days to the moon's cycle. In other words, even though the moon has completed one full orbit around Earth in 27.3 days, it needs about 2.2 more days to catch up and line up with the Sunday. Again for the next full moon. To imagine this, think of it like driving around a circular track. If you were driving around the track, you'd complete a lap in a certain amount of time. However, if someone else is also moving along the outside of the track at a different speed, you'd have to go a little farther to catch up with them and reach the same point again. This is similar to what happens with Earth and the Moon. The Moon has to travel a little longer because Earth's position changes while the Moon orbits. The difference between the sidereal month and the synodic month also explains why the Moon's phases take a little longer. The Moon moves through its phases: new moon, first quarter, full moon, and last quarter, every month. But since it takes a bit longer for the Moon to return to the same phase, the phases are spaced out over a 29.5-day period. This 29.5-day cycle affects how we see the Moon in the sky. If you look up at the Moon each night, you'll notice it changes shape, starting from the new moon phase, moving to the crescent, then to a half moon, and finally reaching the full moon. After that, the cycle reverses and the Moon returns to the new moon phase. This cycle continues every month, and while it's easy to think of it as one consistent rhythm, the slight difference between the Moon's orbital period and its phase cycle shows how interconnected the movement of Earth and the Moon truly are. The reason for the difference in time between the sidereal month and the synodic month is all about the relative motion between Earth, the Moon, and the Sunday. Since Earth is moving through space along its orbit around the Sunday, the position of the Moon from Earth's perspective is constantly changing. The Moon's phases, which depend on its position relative to both Earth and the Sunday, are affected by this motion. So even though the Moon orbits Earth every 27.3 days, Earth's movement causes the Moon to take a little longer to complete its full cycle of phases. This 29.5-day cycle is important for many things. It helps shape our calendars, particularly those that follow lunar months. In ancient times, people often used the Moon's phases to track time and organize events. Even today, many traditional calendars, like the Islamic calendar, are based on lunar cycles. Understanding the Moon's orbital period and how it relates to the phases helps explain why the Moon appears the way it does in the sky at different times of the month. The Moon's 29.5-day cycle is a reminder of the dynamic relationship between Earth and the Moon. While the Moon orbits Earth in 27.3 days, the added movement of Earth through space means the full cycle of phases takes a little longer. This interaction between the Moon and Earth gives us the steady, predictable rhythm of the Moon's phases, a pattern that has shaped human culture and our understanding of time for thousands of years. During the Apollo missions, astronauts brought back around 382 kilograms of lunar rock and soil samples. These samples have been invaluable to scientists, offering a detailed look into the Moon's composition and providing clues about its history. The samples include a variety of rocks, dust, and regolith, each piece telling a different story about the Moon's surface and the processes that shaped it. The Apollo 11 mission was the first to return lunar samples. Astronauts Neil Armstrong and Buzz Aldrin collected soil and rock samples during their historic walk on the Moon in 1969. These samples were stored carefully and returned to Earth for study. Over the following years, the other Apollo missions, including Apollo 12, 14, 15, 16, and 17, brought back more samples, adding up to the 382 kilograms in total. One of the key insights from these lunar rocks is that the Moon's surface is quite different from Earth's. The rocks are made mostly of silicate minerals, like plagioclase feldspar, pyroxenes, and olivine. These minerals form under high temperatures and pressures, which suggests that the Moon's surface has undergone significant volcanic activity in the past. Some of the rocks, particularly those from the Maria, the dark, flat plains on the Moon, show evidence of ancient lava flows. These rocks have a different chemical makeup compared to Earth's rocks, which has helped scientists understand the processes that formed the Moon. For example, some of the rocks brought back from the Apollo missions are basalts. These are volcanic rocks that form from the cooling of lava. By studying the basalts, scientists learned that the Moon's volcanic activity was most intense between 3 and 4 billion years ago, after which the moon's volcanic activity slowed down significantly. This finding has led to the understanding that the moon was once geologically active, but it has been mostly dormant for billions of years. The samples also revealed that the moon doesn't have much water. The lack of water in the lunar rocks compared to Earth's rocks was one of the first major differences noticed. This was important because it gave scientists clues about the moon's formation and early history. Some researchers had hypothesized that the moon might have had water in its past, but the Apollo samples showed that water was very scarce. This discovery has helped shape our understanding of the moon as a dry, barren place that lacks the liquid water and atmosphere that Earth has. In addition to the rocks, the lunar samples also included regolith, which is a layer of loose, fragmented material on the moon's surface. Regolith is made up of tiny bits of rock and dust that have been ground up by impacts from meteoroids and other objects over billions of years. This dust is very fine and sticky, which made it a challenge for the Apollo astronauts. The regolith samples have provided important insights into the history of meteoroid impacts on the moon and the way the moon's surface has been reshaped by these events. One of the more surprising discoveries from the Apollo samples came when scientists found tiny beads of glass within some of the rocks. These glass beads were created by high-energy impacts from meteoroids, which caused the surface to melt and then cool rapidly. These glass beads have helped scientists understand the extreme conditions that the moon's surface has faced over billions of years. The samples also revealed that the moon's crust is made up of different layers. Some of the samples were found to be from deeper layers of the moon's crust, providing insight into the structure of the moon. By comparing the composition of these rocks with rocks from Earth and other planetary bodies, scientists have been able to piece together a more complete picture of the moon's geological history. The Apollo samples have also helped scientists learn about the relationship between the Earth and the moon. By analyzing the isotopic composition of the lunar rocks, researchers discovered that the moon and Earth share a similar composition. This has led to the widely accepted theory that the moon formed from debris created by a giant impact between Earth and a Mars-sized object about 4.5 billion years ago. All these lunar samples have been stored carefully, and scientists continue to study them today. The information gained from these rocks has helped expand our knowledge of the moon and the solar system as a whole. The samples have also been used in many experiments, leading to new discoveries in fields like chemistry, physics, and planetary science. Though the Apollo missions were over 50 years ago, the lunar rocks brought back to Earth continue to provide valuable insights, helping scientists answer questions about the moon's history, its formation, and its relationship with Earth. A blue moon is a rare event that happens when two full moons occur in the same calendar month. This happens because the timing of the full moon isn't perfectly synced with the months on the calendar. A full moon typically occurs about once every 29.5 days, which means there's usually enough time for only one full moon to fit within a calendar month. But occasionally, two full moons can squeeze into the same month. When this happens, the second full moon is called a blue moon. Blue moons are relatively uncommon. On average, they occur once every 2 to 3 years. The exact timing depends on the specific dates of the full moons in any given year. Sometimes, a blue moon can happen in a month that has 31 days, as these months give a bit more room for two full moons to fit. However, it is less likely to happen in months with fewer days, like February, which is only 28 or 29 days long. So, although blue moons aren't a rare event in the sense of being once in a lifetime, they don't happen very often. The term blue moon doesn't refer to the actual color of the moon. Despite what the name suggests, the moon doesn't turn blue during this event. It remains the same color as usual, typically white or yellow, depending on the conditions and the atmosphere. The name blue moon likely comes from the old saying, "once in a blue moon," which is used to describe something that happens very rarely. Over time, this saying became tied to the occurrence of 2 full moons in 1 month. The reason a blue moon occurs is due to the way the lunar cycle and our calendar interact. A lunar cycle, from one full moon to the next, is about 29.5 days long. This means that, in a typical month, there's just enough time for 1 full moon to occur. But in some cases, the timing lines up in such a way that 2 full moons can fall within a single month. The second full moon in that month then becomes a blue moon. The occurrence of a blue moon can also be influenced by leap years. In a leap year, February has 29 days, which gives more room for 2 full moons to occur in a month. This can make the chance of a blue moon happening in February or other months more likely. However, because of the way the lunar calendar works, the blue moon still happens only a few times every few years, regardless of leap years. Blue moons have captured the imagination of many people throughout history. They've been linked to folklore, superstitions, and special events. In some cultures, a blue moon has been seen as a symbol of rare or unique moments. For example, a wedding or another significant life event that happens during a blue moon might be seen as especially rare or lucky. Others may simply enjoy the novelty of seeing 2 full moons in a month, even if they know it's not truly blue. While the phenomenon of a blue moon might not be as dramatic as other celestial events, such as a solar eclipse or a meteor shower, it is still a fun and interesting occurrence. It's a reminder of how the rhythms of the moon and Earth align in ways that we don't always notice, but that can lead to these special moments. For those who love the moon, seeing a blue moon is a rare treat that can spark a sense of wonder and curiosity about the natural world. The moon's gravitational pull has a noticeable effect on Earth's rotation. Over millions of years, the moon's gravity has caused Earth's rotation to gradually slow down, making our days longer. This effect is very slow but steady. On average, Earth's day increases by about 1.7 milliseconds per century. While this change may not be noticeable in a single lifetime, it adds up over time, significantly altering Earth's rotation over billions of years. The reason this happens is due to the tidal forces between Earth and the moon. The moon's gravity pulls on Earth's oceans, creating the tides. As Earth spins, the water in the oceans bulges out slightly, creating tidal forces. These tidal forces, in turn, exert a pull on the moon. Because Earth's rotation is faster than the moon's orbit, the tidal bulge on Earth is always slightly ahead of the moon. The moon's gravity pulls on this bulge, creating friction that slows Earth's rotation over time. In the same way that the moon pulls on the oceans, Earth's gravity also affects the moon. The moon is slowly being pulled away from Earth at a rate of about 3.8 centimeters per year. As Earth's rotation slows down, the moon's orbit gradually increases, meaning it moves farther away from Earth. This slow process is known as it's a feedback loop. As Earth slows, the moon moves farther away, and the slowing continues. This change in Earth's rotation is so slow that it's only measurable over long periods of time. For example, if you were to look at ancient records of Earth's day, such as tree rings or coral growth patterns, you would find that Earth's days were shorter in the past. A day about 500 million years ago was only about 21 hours long compared to today's 24 hours. The moon's gravitational pull has had a constant effect on Earth's rotation throughout history, slowly adding time to each day. This effect also impacts the length of Earth's year. As the moon pulls on Earth, it transfers angular momentum, causing Earth's orbit to gradually change. This transfer of momentum helps slow Earth's rotation while moving the moon farther away. This long-term interaction between Earth and the moon is one reason why our days are slightly longer than they were in the distant past. The impact of the moon's gravity on Earth's rotation doesn't just affect timekeeping. It also plays a role in stabilizing Earth's tilt. Earth's tilt, or axial tilt, is the angle at which our planet spins on its axis, and it's responsible for our seasons. Without the stabilizing influence of the Moon, Earth's tilt could vary more dramatically, leading to extreme changes in climate. The Moon's gravitational pull helps keep Earth's axial tilt relatively stable, preventing extreme shifts and maintaining a more consistent climate over long periods of time. While the change in Earth's rotation might seem small, it's important when you think about it over geological timescales. For instance, if Earth's rotation continues to slow, our days will gradually become longer in the future. In billions of years, the length of a day might be very different from what it is now. But these changes are so slow that they won't be felt for a very long time. The relationship between Earth and the Moon is a delicate balance. The Moon's gravitational pull affects Earth's rotation, and Earth's gravity influences the Moon's orbit. Over time, this interaction has led to the gradual slowing of Earth's rotation and the Moon's slow drift away from Earth. This constant process is a reminder of how celestial bodies are in motion and how their interactions shape the world around us. Even though these changes are tiny from day to day, they add up over millions of years, showing the long-term impact of the Moon's gravitational pull on Earth. The American flag planted during the Apollo 17 mission, the last manned mission to the Moon, is still on the lunar surface. Astronauts Eugene Cernan and Harrison Schmitt set it up in December 1972 as part of their exploration of the Moon. The flag, like the other items left behind by the Apollo astronauts, is still there today. However, it has likely been altered over the years by the harsh conditions on the Moon. The Moon's environment is very different from Earth's. There is no atmosphere to protect objects from the Sunday's radiation. And there are extreme temperature fluctuations. During the day, temperatures on the Moon can soar to around 127 degrees Celsius, while at night they can drop to minus 173 degrees Celsius. These extreme temperature changes would affect any material left on the surface, including the flag. The flag itself was made of nylon, which was chosen because it's lightweight and easy to handle. However, nylon is not built to withstand the intense solar radiation and the drastic temperature changes on the Moon. Over the years, it is likely that the flag has faded or deteriorated due to the constant exposure to sunlight and radiation. Without an atmosphere to shield it, the flag has been bombarded by ultraviolet light from the Sunday, which breaks down materials over time. This exposure has likely caused the flag's colours to fade, especially the red, white and blue that made it so symbolic. The lack of wind on the Moon is another factor that affects the flag. On Earth, flags flutter in the wind, which keeps them in motion. On the Moon, though, there's no atmosphere, so the flag would have remained still. When the astronauts planted it, the flag's fabric was likely stiff and wouldn't have waved like it does on Earth. Some pictures from the Apollo missions show the flag appearing to be in motion, but this was due to the astronauts manipulating it, not wind. Over time, the flag would have stayed in the same position, exposed to the lunar environment. In addition to radiation and temperature extremes, the Moon's surface is constantly bombarded by small meteoroids. These impacts could cause further damage to the flag, adding to the wear and tear it has experienced since 1972. While these impacts are small and don't leave large craters, the constant rain of tiny particles could gradually erode any material left on the Moon's surface. The flag is probably no exception. Despite these harsh conditions, the flag is still there, a symbol of the achievements of the Apollo program. The Moon's lack of weathering processes like wind and rain means that objects left on the surface, such as the flag, are not subject to the same kinds of erosion we would see on Earth. However, while the flag might still physically exist on the Moon, its appearance has likely changed significantly. What remains is likely a faded, weathered version of the bright, bold flag that the astronauts planted nearly 50 years ago. The flag's fate is part of the larger story of the objects left behind by the Apollo missions. Over the years, the artifacts, such as the lunar landers, scientific instruments, and even footprints, have been preserved on the Moon's surface. The Moon's lack of atmosphere means that there is no wind or rain to wear down the materials, and with no tectonic activity, nothing moves or reshapes the surface. The items left by the astronauts are a snapshot of history, frozen in time. However, despite the durability of some of these objects, the Apollo 17 flag will not last forever. As time passes, the constant exposure to radiation and extreme temperatures will likely cause even the most solid materials to degrade. Eventually, the flag will no longer be recognizable, just as other materials left on the Moon will slowly break down over time. But for now, it remains there, a lasting symbol of human exploration, though its appearance has surely changed since the day it was planted. The Moon plays an important role in stabilizing Earth's axial tilt, which in turn helps maintain a consistent climate over long periods of time. Earth's axis, the imaginary line that runs from the North Pole to the South Pole, is tilted at an angle of about 23.5 degrees. This tilt is what causes the seasons. Without the Moon, this tilt could change more dramatically over time, leading to extreme shifts in Earth's climate. The Moon's gravity has a stabilizing effect on Earth's axial tilt. Earth's axis doesn't stay perfectly fixed in space. It can wobble slightly over time, a motion called axial precession. This wobble could cause Earth's tilt to vary by several degrees, which would have significant effects on our climate. For example, if Earth's tilt became steeper, we might have more extreme seasons, with hotter summers and colder winters. If the tilt became smaller, we might experience less variation between the seasons, with milder temperatures year-round. However, the Moon's gravitational pull helps prevent these drastic changes. The Moon's gravity pulls on Earth's equator, which counteracts the natural wobble of Earth's axis. This stabilizing effect keeps the tilt relatively steady. Because of the Moon, Earth's axial tilt varies only by a small amount over long periods, allowing our climate to stay more predictable and stable. This stability is important for life on Earth. The consistent tilt helps create a more stable climate, which has been crucial for the development and survival of life. If Earth's tilt fluctuated wildly, it could lead to major climate shifts, disrupting ecosystems and making it difficult for species to adapt. The Moon's stabilizing effect has helped ensure that Earth's climate has remained conducive to life over millions of years. In addition to stabilizing the tilt, the Moon also affects the length of Earth's day. Over time, the Moon's gravity has gradually slowed Earth's rotation, adding length to the day. This slowing of Earth's rotation has helped maintain a balance between day and night, further contributing to the stability of Earth's climate. The Moon's influence on Earth's rotation and tilt works together to keep our planet in a relatively stable state, which has been essential for maintaining a climate that supports life. If the Moon didn't exist, Earth's axial tilt could fluctuate much more dramatically. Without the Moon's stabilizing influence, Earth's tilt could shift more easily, leading to major changes in the length and severity of seasons. These shifts could make Earth's climate more unpredictable, possibly causing more extreme weather patterns or less variation between the seasons. Such changes would likely have serious effects on ecosystems, agriculture, and human society, as we depend on a predictable climate for many aspects of life. The Moon's influence on Earth's axis is just one example of how interconnected the Earth-Moon system is. The two bodies affect each other in many ways, from the tides to the length of the day. The Moon's gravitational pull has shaped Earth's environment, making it more stable and suitable for life. Without the Moon, Earth would be a very different planet, with a less stable climate and greater fluctuations in its axial tilt. By understanding the Moon's role in stabilizing Earth's tilt, we gain a greater appreciation for how delicate and finely balanced the conditions for life on Earth are. The Moon, though far away, plays a crucial part in maintaining the climate that has allowed life to flourish on our planet. The full Moon is much brighter than Venus when viewed from Earth. In fact, the Moon's light is about 7 times brighter than Venus, which is often referred to as the evening star, because it shines so brightly in the night sky. While Venus does shine with a strong light, the Moon outshines it, especially when it is fully illuminated during a full moon. The brightness of an object in the sky is measured using a unit called magnitude. Venus, which is the third brightest object in the sky, after the Sunday and the Moon, has an apparent magnitude of about -4.5 when it's at its brightest. The full Moon, on the other hand, has an apparent magnitude of about -12.7. This difference means that the full Moon is significantly brighter than Venus. The Moon's brightness comes from the Sunday's light reflecting off its surface, while Venus's brightness is due to the sunlight reflecting off its thick cloud cover. When the Moon is full, it is fully illuminated by the Sunday. During this time, the Moon's surface, which is made of rocky material, reflects a lot of sunlight back to Earth. The Moon is relatively close to Earth, so the amount of sunlight it reflects has a big impact on how bright it appears in the sky. On the other hand, Venus is much farther away from Earth, and though it has a bright appearance, it is not as bright as the full Moon when seen from our planet. This difference in brightness is easy to notice. When you look at the night sky, Venus, though bright, still appears as a small, distant point of light. The full Moon, however, dominates the night sky with its large, glowing presence. When the Moon is full, it's so bright that it can light up the landscape at night, casting shadows and making the world seem almost as bright as daytime. Venus, while bright, doesn't have this same ability to light up the environment in the same way. The brightness of the Moon also depends on its phase. When it's only a crescent or half moon, its light is much dimmer. But when it's fully illuminated, the Moon is far more noticeable. The contrast between the full Moon's brightness and the relatively smaller, but still very bright, Venus shows just how powerful the Moon's reflection of sunlight can be. One reason the full Moon seems so bright is because the Moon's surface is covered with regolith, a layer of fine dust and rock. This material is very reflective, which helps bounce sunlight back toward Earth. While the Moon's surface isn't as smooth as a mirror, its reflective qualities make it much brighter than other objects in the sky, including Venus, when both are visible at night. Even though Venus is often brighter than most stars, the full Moon still outshines it by a large margin. The Moon's brightness is noticeable in any clear night sky, and its full phase light often provides enough illumination to see by, especially in rural areas where there is less artificial light. The difference in brightness is also a key reason why the Moon has been such an important part of human culture, influencing everything from ancient calendars to modern myths and stories. In the grand scheme of celestial objects, the full Moon's brightness can sometimes be surprising to people who are more familiar with the shining presence of Venus. While Venus might appear brighter to the naked eye from certain angles or at specific times, the Moon's size and reflective surface ensure that it outshines Venus overall when it's in full view. The next time you look up and see the full Moon, you'll know that despite Venus's brilliance, it still doesn't compare to the Moon's brightness when both are visible from Earth. The Moon's surface is exposed to extreme radiation because it lacks an atmosphere to protect it. On Earth, our atmosphere acts as a shield, blocking harmful solar and cosmic radiation from reaching the surface. But the Moon has no such protection. As a result, its surface is constantly bombarded by radiation from the Sunday, as well as cosmic rays from deep space. This radiation can be dangerous to both living organisms and any equipment left on the moon. Solar radiation comes from the sun and includes various types of high-energy particles, including protons and electrons. These particles can be harmful to living tissue, especially during solar flares, which are bursts of radiation from the sun. On Earth, our atmosphere and magnetic field deflect most of this radiation. But on the moon, there's nothing to stop it. The absence of an atmosphere means that any astronaut or equipment exposed on the moon's surface would face a much higher level of radiation. In addition to solar radiation, the moon is also bombarded by cosmic rays, which are high-energy particles that travel across space from distant stars and other sources. These cosmic rays are much more powerful than the radiation from the sun. On Earth, our magnetic field deflects many of these particles, but on the moon, they hit the surface directly. This makes the moon's surface an especially hazardous place when it comes to radiation exposure. Radiation on the moon is not just a short-term risk. It is constant. It doesn't fluctuate like Earth's weather or other environmental factors. This steady exposure to high levels of radiation means that without proper shielding, both humans and equipment would face serious risks over time. For astronauts, this could mean an increased risk of cancer, radiation sickness, and other health problems caused by prolonged exposure to radiation. For equipment, such as solar panels, electronics, and other sensitive instruments, constant radiation could lead to faster degradation and failure. To give you an idea of how dangerous this radiation can be, consider the International Space Station the ISS, which orbits Earth, is protected by Earth's atmosphere and magnetic field. Even so, astronauts on the ISS wear special suits and live in modules that provide additional protection from radiation. If astronauts were to live on the moon for extended periods, they would need similar protection. This could involve habitats made from materials that block radiation, such as thick layers of regolith, the moon's surface dust, or even specially designed shielding materials. One challenge with building such habitats is that the moon's surface experiences extreme temperature fluctuations. During the day, when the sun is shining directly on the surface, temperatures can reach up to 127 degrees Celsius. At night, when the sun isn't shining, temperatures can plummet to -173 degrees Celsius. These drastic changes in temperature would require habitats to be well insulated and equipped with temperature regulation systems. Combining the need for temperature control with protection from radiation would make building and maintaining a lunar base quite difficult. There is, however, some good news. The moon's surface is not uniformly dangerous. Areas located in deep craters at the moon's poles are in permanent shadow, and therefore don't experience direct sunlight. These regions may offer a bit of protection from solar radiation, and scientists are currently exploring the potential for using these areas as locations for future lunar bases. In these shaded regions, the lack of sunlight might also provide more stable temperatures, making them a promising option for shelter even. So, radiation remains one of the biggest challenges for human exploration and habitation of the moon. Any future lunar missions, especially those aimed at long-term stays, will have to account for the radiation hazard. This could involve building habitats underground or using regolith to create thick walls that protect astronauts from the constant bombardment of harmful particles. Until effective ways to protect against radiation are developed, any humans living on the moon will have to be well shielded from its harsh and dangerous surface environment. Recent studies suggest that the moon may have a small, molten iron core similar to Earth's, though much smaller. This idea challenges some of our previous understandings about the moon's interior. Scientists have long believed that the moon's core was mostly solid, but new data from space missions and lunar samples point toward the possibility of a small, liquid, iron-rich core. The moon, like Earth, is made up of several layers: a crust, a mantle, and a core. Earth's core is mostly iron, and it plays a crucial role in generating Earth's magnetic field through a process known as the geodynamo. In the past, scientists thought that the Moon's core was too small and too cool to generate a magnetic field in the same way. But recent findings, including data from NASA's Grail mission and other studies, suggest that the Moon's core might contain enough liquid iron to generate some form of magnetic activity, even if it's not as strong or widespread as Earth's. This discovery comes from studying the Moon's magnetic field. The Moon doesn't have a global magnetic field like Earth does, but some regions of its surface, especially in the crust, show traces of magnetism. These magnetic anomalies have puzzled scientists for years. The idea of a small molten iron core offers an explanation for these magnetic features. If the Moon's core is partially liquid, it could have produced ancient magnetic activity. This magnetic field, though not strong enough to be detected today, could explain the leftover traces of magnetism found on the Moon's surface. Another clue comes from the Moon's seismic data. Seismometers placed on the Moon during the Apollo missions recorded moonquakes, some of which appeared to be caused by movement deep within the Moon. These readings suggest that the Moon has some internal heat, which would be necessary for a molten core. This heat could be left over from the Moon's formation, or it could be generated by the slow decay of radioactive elements in the Moon's interior. Either way, the presence of heat in the Moon's interior supports the idea of a partially molten core. If the Moon does have an iron core, it would not be as large or as active as Earth's. Earth's core is responsible for much of our planet's heat and magnetic field, but the Moon's core is likely much smaller and less active. The Moon's size and lack of a strong magnetic field suggests that if it does have a molten core, it would not be generating a global magnetic field like Earth's. Instead, any magnetic activity would be localized and much weaker. The idea of a molten core also provides insight into the Moon's formation. The leading theory of the Moon's origin is that it formed from debris after a Mars-sized object called Theia collided with Earth billions of years ago. This violent impact could have melted parts of the Moon, leading to the formation of a partially molten core. Over time, this core may have cooled and solidified, leaving behind the Moon we see today. Scientists are still investigating the Moon's core, and there are many questions left to answer. For example, how much of the core is molten, and how much is solid? Does the Moon's core still produce any magnetic activity today, or was it only active in the past? These are questions that will take more research and data to fully understand. The idea of a molten core changes how we think about the Moon's history and interior. It suggests that the Moon might be more geologically complex than we once believed. If the core is indeed molten, it could provide new clues about the Moon's early conditions and the processes that shaped it. As technology improves and more data is gathered from missions to the Moon, we may learn more about its interior and how it compares to Earth and other planets in the solar system.